Hey everybody, my name is Samrat Kishor and I welcome you all to the Baseline Show. We're doing this very special episode, which is a second episode of Zero Knowledge Proof 101 Basics in collaboration with C4, and we are also co-streaming on their channels. As always, I would encourage you to read more about Baseline Protocol. It's a protocol which is aimed at creating a secure and private way for organizations to sync up data points amongst different systems of record. Organizations can communicate, collaborate on shared business processes, for example, supply chain and financial reporting. So, with me, I have today some very special guests. We have Josh from C4. We have Andreas, who's going to be our speaker today. He's also the co-chair of Baseline Protocol, along with me. And we also have Mark Hattel and Mark Remza. Hi everyone. Thank you for making it to today's show. I know the festive season has kicked in, and you've taken time out and doing this. So I hope people who are watching us and people who will watch us in future do spend some time in learning. Enjoy this downtime, pick up more skills. We also have Manik Jain. He's with us. He's part of the Baseline TSC as well. He's not on video today, but he is going to be contributing to today's show. One of our he's one of our very well established core devs. We are also looking forward to hosting Jessica sometime soon from C4. But I would like to now invite Josh to go ahead and introduce C4.
Hey everyone, thanks for having us again. We're excited to do these co-live streams. Pretty great. C4, or the Cryptocurrency Certification Consortium, is a nonprofit that's been in the space since 2014, and our focus is on helping standardize the space to kind of add consistency across all the different wonderful services and software that are out there, as well as focusing on educating people, making sure that all these different kind of weird, technical sounding, terrifying topics are laid out and help people to kind of excel in this space with this type of knowledge. So I'm one of the co-founders of C4, and we've got our executive director Jessica on with us as well. Jessica, welcome. And we're looking forward to talk about some ZKs.
Excellent. Thank you so much, and we really appreciate what you're doing. And yeah, with that, deep dive a little. Let's deep dive into CK things. Last time, okay. Hi, John. Thank you very much for watching us live. So last time we had some technical glitches. So what we're going to do is we're going to do a quick recap of what we were covering last time, and then we're going to deep dive into newer topics for today. So I pass it on to Andreas. Go ahead, please.
Yes, so thank you, Josh, Jessica from C4, and Samrat, my co-conspirator at the Baseline Protocol, as well as Mark Howell, the effervescent outreach TSC guru, and Mark, the primary R&D on all things baseline and business process automation. So thank you. And shout out to the omnipresent, it seems, John Wolpert, who's watching the stream. So just a quick reminder. So last time we talked about why do we need zero knowledge proofs, right? In fact, we have the Baseline Protocol published a blog around the digital business trilemma. If you're interested in finding out what that is, the digital business trilemma, check out the blog. I don't know, Samrat, whether you can post it in the chat so people can can have a read, but basically we're talking about zero trust multi-party
Definitely.
coordination under zero knowledge, where zero trust is really important. Why? Because um, uh, zero trust is the new it word in cybersecurity, because if you want to do dealings with the government, you must now implement zero trust, um, which means every single interaction is assumed to be untrusted. So you have to establish trust every single time you interact with someone, with everything. So that's and the only way to do that is in the end through zero knowledge, because that allows to establish also zero trust. So again, really brief. So again, for those of you who weren't there last time, really zero knowledge is basically just being able to prove something um, to someone without revealing what that something is, right? Like the password to Alibaba's cave. I walk into the cave, open one way, open the door, not revealing the password to anyone, obviously, and walking out the other side. So I have proven that I know the password to Alibaba's cave by walking in one side, coming out the other, but I haven't revealed anything. So that's the short summary of where we left off last time. So what I want to do now is talk a little bit, go a little bit deeper, and talk about actual applications, um, you actually to support and execute actual use cases. So let me do that. I'm actually not going to share my screen. I uploaded the presentation. So you just need to see whether you need to tell me whether you're able to see that presentation. There we go. Looks like let's talk about zero knowledge use
There we have
cases.
it. Yeah.
So just a reminder, so we have this new ZK enterprise stack where we increase our security as we go down from the top, which is fully centralized, down to the bottom, which is the public blockchain, which is decentralized, the level of which we can debate, but the security definitely increases. I don't know of any instance where either Ethereum or Bitcoin have ever been successfully compromised. If you do, let me know. I haven't. And given that it's always open and accessible by anyone, that is quite an accomplishment. No other computer systems in the history of humanity can claim that. In fact, even non-computer systems they always have been compromised. So this is a first in human history, really. However, public blockchains are, as John Walpert so aptly coined, are public data nudist colonies. So privacy really is bad down here, but increases as you go up. Also, the speed increases. You can get more computations done in the top layers of the stack rather than on the public chain, because slowness is good, because slowness means more security. Obviously, control also increases, because up here everything is centralized. Down here it's decentralized, which means less control for the individual at the bottom, more control on top. So our three top layers are really what you would call the traditional enterprise stack. And then we have our magic layer of privacy and speed, the processing layer in the middle, that is then sitting on top of a public blockchain. If that looks familiar to some, yeah, it's not really we have seen these type of multi-layer architectures in many instances before. However, this is the first time where we're sort of like marrying centralization and decentralization in an effective way. So moving on, so you saw that last time too. Now we're going here. Reminder: what is so magic about the magic layer? Well, we have privacy, so we have zero knowledge, proofs of transactions. We have strong encryption. We are using the latest cryptography techniques. Even though when you speak to Microsoft research guys and they say, "What? It's less than 30 years old," that's not good. But apart from our very conservative cybersecurity friends, we then also have the security aspect, because it inherits the security assurances from the public chain, which is uh, important. And the asset data or any data is directly available on the public chain um, uh, to be used, which is important. However, at the same time, it doesn't reveal anything. So that's the apparent paradox that we're resolving using zero knowledge proofs. And because we have this centralized stack on top, we can increase speed, which means we can roll up all the transactions that we're doing on the centralized part and then anchor it on the public chain. That means less cost than if we're doing every single transaction on the chain. The good thing is we have verifiability. Why? Because all those zero knowledge proofs of all the transactions that are happening on our layers above can be verified in zero knowledge on the public chain, which means you can actually prove that no one cheated on that on that on those layers above. You might not like them, but you can prove that they didn't cheat. Everything was done correctly. Therefore, our magic layer has, again, the same security assurances as the public chains that we like. It's 100 to 1,000 times more scalable, which is what we love. You have guaranteed data availability on the chain, which is awesome. Which allows you to have the same security properties. You have privacy preserved at all times. It's much less transaction fees, verifiability of all proofs, and that also, because it's the top part is centralized, you can do KYC and AML. Well, that sounds like it's you got the cake and eat it too, right? Not quite, because it's definitely not transparent, which is not supposed to be, and it's not necessarily censorship resistant. So that is also that's also okay, because and when we're talking about enterprises, we trust the operators. And by the way, most layer twos actually they're not decentralized. They have centralized sequencers, centralized provers. So it's like no one should get their underwear in a bunch. So let's move on. So what type of ZK proofs do we need for the magic layers, right? So proofs must be efficient, succinct, and verifiable on a public chain. Efficient and succinct. Why? You don't want proofs to be kilobytes or long, because that costs a lot of money to store. And if the proofs verification take long, that means a lot of compute cycles, and compute cycles, as we all know, cost also money on the public chain. So therefore, if you want to be able to verify proofs fast, they must be fast and they must be short, such that we're not paying an arm for a leg, because otherwise it wouldn't really be worth our while if we're not gaining anything, right? Proofs need to be recursive, right? We'll see in a second why. basically you need to be able to prove a zero knowledge proof into another zero knowledge proof, because in, for example, a supply chain, as our lovely friend Mark Haddle will tell you, no one wants to share any data, but they need to prove everything. So that leads to sometimes really not only awkward but really bizarre circumstances. My favorite thing is that Chinese steel is exported to Vietnam and then imported to the U.S. as Vietnamese steel, even though it's Chinese steel. So that's that. Proof generation needs to be fast, because otherwise you can't get really that much speed in our magic layer. So we need to figure something out where proof generation is fast. And then we should ideally have no or limited number of trusted setups, right? So trusted setup is basically generating some cryptographic toxic waste that you need for your prover system to work. But that allows you to typically have very efficient and succinct proofs. But if you don't have that, then your proofs are larger. They're faster to generate, but they're larger, and therefore your verification time is longer and costs more money. So there are all kinds of trade-offs. So that's why, can we limit our numbers of trusted setups that we can that we can use, or even get rid of them? So those are our criteria that we need to fulfill in order to be able to be fast and cheap and secure. Right? We're definitely cool because we're using ZK. So that's by definition, ZK is the new meme. It's like I said, anybody know of a ZK coin yet? That's like any meme coin that has taken off yet? I don't think so. But if you know, let me know, or launch it yourself. Right? There are enough gullible people out in the world that you can get away with that. It's meme coins. It's all there is. Zcash is a native protocol token, right? So that's required. That's a necessary requirement for the system to work. So protocol tokens are not meme tokens. Meme tokens is I don't know, sushi swap tokens.
Yeah. We'll try
Right,
and prove to you that we know of a token.
right. There are all kinds of like interesting things. Anyway, Zcoin, where we have no idea what it does. That is exactly right, Sonal. I think that's brilliant. It's
Just prove
like
their wealth, prove the value.
that is what is it? I don't know. We're not telling you. What is it useful for? We don't know. It's zero knowledge. Brilliant. All right. So yeah, I think the world's ready for a ZK token. So now that we have our requirements, we know we want this stack because it does all the nice things. So how do we actually get there? So what's a way available? Do not, common ZK prover systems do not fulfill all 4 requirements. More advanced ZK prover system mostly fulfill all 4 requirements, except for one little thing. But important detail: public blockchains support of the crypto used. That is a very limiting criteria. Why? Is because in order to verify proofs on chain, you need to do these cryptographic operations, and if you do them like in a smart contract, they take a whole lot of cycles and they're very expensive. So back in 2017 or 2016, 2017, when Zcash started up, Zuko and and cohorts. And so Zuko, Vitalik, and Christian, they were like, we got it. Christian Riedwieser, in case you don't know. They were like, oh, we want like Zcash on Ethereum and Ethereum on Zcash. How we can do that? So they were basically talking about a bridge. So it's like, yeah, well, we need to be able to verify the proofs that are generated on Zcash on Ethereum in order to generate a wrapped Zcash. So, and lo and behold, in order to make it cheap, Christian wrote the precompiles that are currently there for pairing friendly curves, because Zcash wasn't, so is using zk snarks, which require what's called bilinear pairings of elliptic curves. That's something for the crypto nerds out there, the cryptography nerds, not the token nerds. So guess what? Those precompiles were implemented. Try that to do now, right? No chance. No chance. It's like the core developers will show you the middle finger nowadays, but back then, it was still less structured, more free for all. So, but if those precompiles hadn't been written with a particular curve in mind, because it was used, that curve was used by Zcash back then, we wouldn't have ZK rollups at all. We would probably only have optimistic rollups, and we wouldn't be talking about this enterprise ZK stack. Wouldn't be possible, because we would not have a public blockchain that is able to verify zero knowledge proofs in a decentralized manner. So sometimes the fever dreams over beer and vodka actually lead to something beautiful. Not always, but sometimes. So let me move on here. I've already spoken too much. So let's give an example of the John validity proofs are the proofs that are being put on chain. Those are validity proofs. They're not fraud proofs. That's what the optimistic rollups do, and that's why it takes so long. Validity proofs are directly proven on chain and finalized. So you have immediate data availability. That's why. So, but now really, they aren't zero knowledge. The validity proofs aren't zero knowledge, but that's why I'm talking about ZK rollups, John. You know that. So, because we want privacy and speed. Thank you, Monique. So it's like, how does ZK rollup work? Right. So what is a ZK rollup? It's a ZK rollup that is actually anonymous. When does full ZK is the question. It's soon. It's like ZK EVMs. I'll talk about that. Are coming out right now, and there's great work in optimizations going on there right now. But let's focus on this little piece here. So how do they work? So we need to be able to obfuscate everything. So what do we need? We need 2 trees, actually 3. But let's start with 2. We need one tree that shows you what the state of your asset is, right? That's why it's called the node tree, because every node represents an asset that can be spent, and that is actually fully encrypted, and only the asset owner can decrypt that. And then there's a nullifier tree, right? Because you're adding leaves to the node trees, and then you need to, when that leaf is no longer valid, you need a nullifier leaf that corresponds to a leaf here. So how does that work? So how does that work? So the asset is valid, and then there's a you're spending it, so there's an old leaf, and now you're creating a new leaf. When you create the new leaf, you need to create a nullifier leaf to nullify the old leaf. And because you have when the asset is sold, you need to destroy a token that is associated with the that you exchange the asset for, and therefore you need to destroy a token here. Because in this case, the token represents some fiat currency, so you need to destroy that, which means you need to create a new leaf. And if you destroy something, or if you sell something, you create something, you need a nullifier. When you change something here, you need a nullifier leaf here. So you have our node tree and the nullifier tree. So when new leaves grow here, new leaves have to grow here as well. There are some details in here I'm not going to go into, but that's basically it. There's a new leaf here, the old leaf creates a new leaf here, and then you can see that the old leaf is no longer valid because it has a nullifier. Right? It nullifies the previous state. Well, I was not entirely truthful. There are actually 3 trees, right? So when you're and you need, because you need to keep track of the state of all trees, right? There, because when you add a leaf to the tree, it's no longer the same tree, right? So, but you need to know that, your old trees were all basically done in the right order, right? You have to maintain the state history, right, of all of your transactions, since everything's obfuscated to everyone else except the parties in the transactions. We need to make sure that we keep track of everything. So that's why we have these trees, these Merkle trees. So you have the old tree, the old node tree becomes a new node tree, and then you need to register you have the that in the old root tree, and then you have the old nullifier tree that's also added to the old root tree, and then you also have the new nullifier tree, and the new nullifier tree and the new node tree together create a new root tree. That's a new leaf added to the old root tree. So, and that tracks the history of all the nodes and nullifier trees. And because everything's encrypted except at the time of transaction when 2 parties interact with one another, boom, you have full anonymity. Now, how does that? Now, that is, again, that's happening in our magic layer of privacy and speed, right? That's where the trees live. But how do they get onto the blockchain, right? So how do we do that? Reloading. We're doing batching, right? So we have a ZK state machine. We have our circuits for each transaction. That's actually done on the user side, and all those transactions, they can actually be computed in your browser, or in your mobile app. They're sent into the magic layer into the processing layer, where you're batching them up, and you're batching into and transactions are put into a batch for processing reasons, so you can parallelize the whole thing. Wonderful. And then you take those K batches and you batch them up again, and all of that is then generating one final transaction that is posted on chain. So it is actually full. So you have digests of zero knowledge proofs, very short, that are then all rolled up. There's some recursiveness happening here as we're proving that all those ZK proofs here were actually done correctly. So I'm proving every single proof here in the batch, and then the batch generates a zero knowledge proof that is proved also recursively here in that final batch. So we have multiple recursive proofs put together, and that is put as one proof and one proof only onto the public chain. And voila, you have full anonymity of transactions on the chain. Now, the keen observer has probably figured out, well, we're talking only about assets and asset states. So yes, this is what you would call a UTXO model, an unspent transaction output model that we know from our Bitcoin days. So doing that as a general purpose computation, that is a lot more tricky, right? So let's see where we are with that. And let me run through that really quickly, and then we can take some questions. So this is done in what's called a ZK EVM, right? So what's the ZK EVM? It's just like a normal layer 2 ZK rollup. However, it now allows you to use Solidity contracts and deploy them on an EVM, and it takes the bytecode that you of the Solidity contract, and just like a normal compiler does, and translates it into opcodes. And those opcodes you can find in Gavin's yellow paper, and a few ones have been added. And these opcodes are then with the inputs and outputs are atomistically proven with zero knowledge proofs. How that works, one second. The really important thing here is you can use your existing tool chains, right? So nothing changes. You want to run Uniswap v3 on a ZK EVM? Go ahead. Deploy your Uniswap v3 smart contract system and run it. You want to bridge assets now from Optimism to Optimism Uniswap v3 over to your ZK EVM? Not a problem. Use a known bridge, and you're onto the races, right? So that's actually pretty cool. So now I have general purpose compute in a with my smart contracts in a ZK environment. So how does that work? You have all your transactions that are sent to your layer 2, where they can actually in parallel be processed and then batched up and put as a rollup block onto the public chain, just like any ZK rollup would work. If we're looking a little bit under the hood, what do we see? Let's do a little bit of a lifecycle walkthrough. The user submits transactions using, for example, MetaMask, right? It's a regular smart contract, so the usual JSON RPC interfaces all work. And we have, yes, we do have a mempool. And then we have something which is unique to layer 2s. We have a sequencer. A sequencer basically orders your transactions based on some rules into a sequence, and submits a digest of those transactions on the public chain. That's a commitment. The aggregators that have been lurking in the background are watching the chain, and are grabbing the oh, there's a digest. Oh, okay. Where do we have all of that detailed information? Well, it's in our data store. Why is it in the data store? Because the sequencers have exchange that have put it there, and the synchronizers have made sure that the data that's on chain and in the store stays in sync. So the aggregators, when they grab it, they know that digest that it was posted here corresponds to a specific set of transactions here, which they're grabbing, and then they are hitting the prover. The prover, we'll talk about that in a second, generates all those lovely zero knowledge proofs for a transaction, because a transaction is not just one zero knowledge proof, but a whole bunch, because one smart contract transaction might execute a few hundred opcodes. So you have a few hundred zero knowledge proofs that you need to batch and roll up and post on chain. That sounds like a lot, and it actually is, but there's a trick, and we'll talk about that trick in a second. But once that final zero knowledge proof is posted on the Ethereum chain for the digest, and is finalized there by validating that proof, we're all done, right? So let's take a one more detailed look under the hood. What do? We have the node, which is here, which is the aggregator that grabs the data, which is organized into a Merkle tree, and sends the input to the ZK prover. The ZK prover takes that, also grabs more data here, generates the proofs, and sends it back to the node. Great. Come on. So then what happens? Then you have that ZK prover is just like the EVM. It is a virtual state machine. And what they're doing is that in order to get this in any way, shape, or form manageable, you have multiple state machines that are doing specific things. So you have a main processing manager, so to speak, that is basically divvying up the work to very specific state machines that are generating zero knowledge proofs for very specific things like arithmetic operations, binary operations, memory operations, computing the Kekchak hash. There's storage, and then there's some auxiliary state machines that are sort of like helper state machines that are called by these secondary state machines. So if this looks like a microprocessor architecture to you, you're 100% right. It is. It's actually quite a brilliant this type of architecture. This is obviously very stylized, simplified. This is actually much more complicated. But as microprocessors are, right? But this is some brilliant architecture work that the various teams, whether that's Consensus Software Inc. or Scroll or Polygon Hermes or Matter Labs with ZK Sync 2.0 and a few others have done absolutely brilliant work. Kudos to those teams. Brilliant engineering work. So how does these things work? As you see, this is actually microprocessor architecture. You have your control unit, you have the main memory, and the ALU. As you see, that's exactly how this works, right? So the way that I described it, just like a regular CPU. Now, this is the last one. This is specific to Hermes. There are different types of solutions. Others are taking Consensus Software Inc. takes the actual opcodes and and does not change anything. So that's what Vitalik would call a type 2 ZK EVM. Hermes does it differently. They're transpiling the opcodes into ZK friendly opcodes, and are then taking those and computing specific commitment polynomials for these optimized opcodes. Those are trade-offs. There's one is closer to the actual EVM than the other. Each have their advantages and disadvantages, but the basic thing is here is you have the compiler output that is put into the ZK executor that generates Stark proofs, a whole bunch of ZK Starks, which are cousins to ZK Snarks. The proof generation time is very fast, but the proofs are much larger. So so what do you do? You are generating all of these snarks from all of these opcodes and proofs, and then you're generating a witness, the witness you need to prove completeness, which you're generating from the proofs and the public inputs, and you're computing the verification keys and everything. And that witness goes then into for all these snarks, right? They're then batched, and there are proofs generated, just like in the ZK rollup example, which is, by the way, AdStack. Love AdStack. AdStack are great. They're doing wonderful work. I forgot to say that. Shame on me. And here they are going and saying, hey, we cannot put Starks and verify Starks on chain because that would be really too expensive. They're great because I can compute a lot of proofs really fast. So what do? I take the Starks, I batch them, do a recursive Stark, batch them again up just like AdStack does. And then this is the really cool thing, I can actually prove a ZK Stark inside of a ZK Snark. And a ZK Snark on the right elliptic curve can be verified on chain. So with that last trick, I'm now rolling up all the Starks and creating a prover, a ZK Snark proof of all of them, and put that on chain. And that is my validity proof that is going to be put on chain. Now, did I tell you that this is ZK? No, it's just a ZK rollup. However, the digest, which is committed by the sequencer, can be put into zero knowledge. So this digest could be zero knowledge proofs. That's the next step. You're putting zero knowledge proofs into the digest, and then you verify that those are correct. Right? And you just need asset identifiers, and then you're good. At that point, you also then have full privacy, because when you exit, when you pull out your assets, you just need to show that one of those digest proofs is actually controlled by you. And then you can pull that asset out based on what's on the information that's on the layer 2. And because this is general purpose, and this brings now us full circle back to baseline, the ZK EVM, if you're doing some privacy modification on the digest, can be an execution framework for the baseline protocol in a way that is standard compliant. And that's it.
Awesome, Andreas. Thank you very much for that presentation. I think that's probably the best presentation I've seen on this topic, and really mind blown. For example, I could really wrap my head around the the work which Hermes is doing. For example, I mean that's something new, and I'm just okay. Awesome. So yeah, let's take some questions. The chat has been very lit today, so exceptionally lit today. So I'm happy that there are people watching and engaging. So yeah, let's take some questions. Thank you, John. Much appreciated. Andreas, kudos to you. That's probably the best, most succinct presentation I've seen on this topic.
Sorry, it took a little longer, but it's like I couldn't stop myself from telling a couple of stories on the way.
That's super.
To answer Ruben. So the Starks are quantum compute safe. Snarks are not. But as soon as you write precompiles for Stark proofs, then yes, that whole thing on chain is also then going to be quantum secure if your chain is quantum secure. If your layer one is. So it's that's going to be an interesting transition. But before we get to that point where you can do 256 qubits computations on CACJAC and digital messages on yeah, it's like that will take a little while, a few decades. Oh yeah, we can post a snark on Ethereum, John. All right. Any further questions? And thank you, everyone. Mark, you're talking and you're on mute, or I can't hear you.
Oh, there we go. Can you hear me now?
Yes.
Could you talk a little bit about what it might look like to put a baseline workflow through a ZK EVM? And maybe what the standard development process could look like for that?
It's just so basically what you're doing is you're actually now adding additional ZK proofs to your call data. So now you can actually have recursive proofs, right? So because in the EVM, I can prove the input in the call data, which is the ZK proof, right, with the precompiles. So, and then I have proved the ZK proof in the EVM, and I have generated proofs that I proved that proof was correct. And then on chain, I prove that everything is correct. So yes, I can then start building proofs upon proofs upon proofs if I'm structuring my smart contracts correctly. So that's the one. But I think there was one more question, wasn't there? Is it possible to rep contextual ZK hashing into date variables within a JSON versus an entire transaction? Yes, as I just said, you can write a smart contract functions that accepts call data, and the call data can contain your witness. So there you go. Can you, Samrat? I think Joshua wants to say something, but I think he's muted.
Yeah, I muted everybody.
No, muted now, but just for the future, I'm good. Although we did get a question on the C4 stream. Is there a question, or is there or do you think there will be in the future a competitive advantage to a specific ZK protocol, or do you think they'll kind of hit parity in the long run? And that question was from J5L.
So, Jay, the answer to that is no, because they all have trade-offs, right? You need to pick the prover system that is best suited for what you're trying to achieve, right? If you want specific performance and you want speed, you're handcrafting your circuits, because they will be definitely faster and require less memory, etc., than ZK EVM. If you're going for more general purpose stuff and you're willing to incur the cost of compute and storage, you go ZK EVM route. So it's really dependent on what you're trying to achieve, which is, by the way, true for any technical solution. There is no one size fit all, or one prover system will rule them all. No, prover system evolve just like technology evolves. They're getting better, and they will have trade-offs, just like normal technology has. And you have to decide which one is best suited for you. There are many different prover systems out there, each built for very specific things, right? I mean, so you need to go out, do your due diligence and understand, and ask the right questions when you of the teams that are proposing solutions, and let them know what the trade-offs are you're willing to take or not.
Okay, there's some more question.
So let's take a normal data packet and ZK all the things. But well, so ZK is a proof of correctness, right? So if I take data, right, then I need to have an assertion, right, that the data is correct. At that point, I'm back to my root of trust problem, right? And then however, what I can do, I can generate a circuit that verifies the signature on a verifiable credential over that data, where a known entity claims that data is correct. That is doable. That's actually relatively straightforward and simple circuit. It's just a signature for verification and over a hash. So, but again, it's a proof of correct execution. It's a proof of correctness. Was this program? So basically, ZK proofs are nothing but translating computer programs into an optimized language that allows you to prove correct execution under zero knowledge for a given input, without revealing the input, or at least most of the input. And then Q4 was what? Is there any reason why someone could hash ZK UUIDs into, say, the audio frequency spectrum in pursuit of a stickier? Maybe. I haven't really thought about it. It's like that's too much for me to process. I cannot generate. I will send you a ZK proof later on that.
Will it be fast enough? Yeah.
Yeah, it will just say it is doable. Right? That's like the old joke with the engineer, the physicist, and the mathematician that have been given a can of food, and they had to open it, otherwise they would starve, right? And the engineer and the physicist survived because they were practical, and they open up the cell for the mathematician, starved to death. All the walls are scribbled with an intricate proof. At the bottom right corner is says the can can be opened, QED. So that's I'm sure it's somehow doable.
All right. So yeah, I think we're at the end of a rather interesting show. And yeah, thanks for all those questions. Everybody who was watching us and engaging in real time. And yeah, there are slow claps. Um, there's laughter. There's a lot of emotions that we take back from today's. But very importantly, what we take back is a great video which we will use for a very long time for educating people on the subject. And yeah, we can continue, as we just posted, so we can continue chatting. If anybody has any questions in future as well, do find us on our Slack channel, and you can hit up Andreas, and ask any questions. um oh yeah, somebody says, yeah, he's hilarious. Yes, Andreas is the right mix of knowledge and humor. All right, so
Thank
with
you, Michael.
that, okay, and we also pinned one message which was ZKVM block coming. So that's something which Sonal said, and yeah, I totally believe that it's one of the topics which we will pick up and we'll publish on that very soon. Okay, so with that, it's a wrap for today. Thank you everyone who tuned in, and see you next week. We will just have office hours next week. We will chat a bit about everything baseline, and we'll just say, see everybody off into the holiday season, and then we will meet next year. All right. See you, everyone.